Hi, I'm Sagar Karandikar. I'm a PhD student at UC Berkeley and a student researcher at Google, and I'll be presenting CDPU, co-designing compression and decompression processing units for hyperscale systems. This is work done in collaboration with several folks at Berkeley as well as Google. Lossless data decompression and compression are used widely in warehouse-scale computers, primarily for two use cases, to reduce storage and memory consumption and to reduce data transfer costs. Compression and decompression are unique amongst the data center taxes because unlike most data center taxes that are required for distributed application functionality, compression and decompression are used optionally to trade off resources in warehouse-scale computers, like CPU cycles, storage, network bandwidth, and memory. As a first step in this study, we profiled Google's fleet-wide usage of compression and decompression to understand specialization opportunities in terms of offloading, acceleration, and enabling new capabilities in the data center. We first found that about 3% of fleet-wide CPU cycles at Google are spent in compression and decompression. Certain services spend nearly 50% of their time in Google's fleet in compression and decompression. But most importantly, 95% of bytes compressed in the fleet use less capable algorithms, presenting a large opportunity for hardware specialization to change warehouse-scale resource trade-offs. As a first step towards evaluating CDPUs in hyperscale environments, we build HyperCompressBench, an open-source hyperscaler representative compression benchmark suite that represents Google's fleet-wide usage of compression and decompression. We then build a CDPU implementation and design space exploration platform where we implement CDPUs as chisel RTL generators and integrate them into chipyard-generated RISC-V SoCs to evaluate the feasibility of CDPUs in a hyperscale context. These implementations are highly parameterized, enable us to explore various placements and various parameters of the CDPUs themselves. Our extensive design space exploration methodology begins with the CDPU RTL as the single source of truth. We then feed this RTL into FireSim to get cycle-exact performance measurements running HyperCompressBench benchmarks. And then we feed the RTL into Hammer to obtain ASIC QR metrics for a commercial 16-nanometer class FinFET process. All of this design information is then fed back into the RTL and captured in the RTL, which is open sourced, and this entire process, excluding ASIC QR metric collection, has been reproduced by artifact evaluators. Join us at the full talk in ISCA Session6B Cloud at 2:45 p.m. on Tuesday, June 20th, where we'll talk about many of the lessons we learned about hyperscale deployment of CDPUs using our design space exploration methodology and profiling information. See you there.